So now let's learn some of the most common dynamic programming patterns. And let's start with the 0-1 knapsack pattern. And we're going to start with an example that's pretty much the most cookie cutter knapsack example that we could come up with. But there are examples that can get even more complicated than this. But I think understanding the basics will make it a lot easier when you encounter like a more complex version of this problem out in the wild. The idea is that we're given some kind of bag or backpack or knapsack, something with a fixed capacity. Suppose this is our backpack, and in this example, the capacity of it is 8. It could be, 8 pounds, 8 kilograms, it'd be something. And we're also given some items over here. Each item will correspond to a single index. We have 2 arrays though, so for each item, we have some profit value that we want to maximize. And we have a weight value, and this weight is going to affect how much we can carry in the bag essentially. The bag has a capacity of 8, but each item has some weight to it, so we can't necessarily take every single item and put it in the bag. But this problem is that we want to maximize the total profit that can be contained in this bag. Another variation might be we want to reach, the exact capacity. We want to determine, can we reach this capacity or not given these items? But in this case, we just want to maximize the profit while staying within this capacity. The reason this is called the 0-1 knapsack though is that for every single item, we can either choose to include it, aka we can choose to include one occurrence of that item, or we can choose to not include that item, meaning we include 0 copies of that item. There's another variation of the knapsack problem that we'll be talking about later. It's called the unbounded knapsack, and that's because for every item, you can include it an infinite number of times, basically as many times as long as we don't go over our capacity. That's the idea at least. But for now, let's focus on the 0-1 knapsack. Now your first instinct might be to just be greedy. Why not just take the items with the maximal profit and then keep doing that until we fill up our bag? Well, let's see what would happen with this example. We'll choose the one with a profit of 7. So our profit so far is 7. Our bag though has a 3 in it. Next, we'll choose maybe this 4. There's a tie between these two, so let's just arbitrarily pick this one. We add 4 to our profit, but the weight is 5. So now we have 2 items in our bag, weight 3 and weight 5. We filled up the capacity. We can't add anything more. So the total profit we got was 11. Is this the solution? Is that the maximal profit we could have possibly gotten? The answer is no, actually, because we can actually not include that item and include these 2 items, which will give us a profit of 7 plus 4 plus 1, which is 12. That's bigger than 11. And actually these 3 will stay within our capacity as well. We'll have a total of 6, whereas our capacity is 8. So that's why greedy doesn't work. And you can probably think of some other examples where it will fail as well. In some cases it might work, but it's not guaranteed to work. So maybe we need to try a brute force approach. When it comes to dynamic programming, starting out with the brute force is not a bad idea. So let's try to think about this in terms of choices. We initially start out with a capacity of 8. So for this item, we have 2 choices. We can include it or not include it. If we do include it, it has a weight of 5. So our capacity then will be decremented by 5. Our capacity remaining will simply be 3. If we don't include it, our capacity will remain the same. So it'll stay 8. But when we include the item, we gain a profit of 4. If we don't include the item, we gain a profit of 0. And for every single item remaining, we're going to do the same thing. We're going to have a decision to include it or not include it. So this is basically going to be a binary decision tree, 2 branches for every node. Now the height of the tree is going to be n, because for every single item, we're going to have a level in the tree. So n is going to be the size, or basically the number of items we have. So the size of the tree is going to be 2 to the power of n. So this is not a super efficient solution, but let's just run through it quickly because it will help us get to a more optimal solution. So at the second item, we can choose to include it or not include it. And we can do that for both of these branches because we want to go through every single possibility. So if we include this item, it has a weight of 2, so we would have a weight of 1 remaining if we chose to include it. If we don't include it, we'll still have our weight or a capacity of 3. That's what I meant to say. We'll have a capacity left because we're adding these values to some bag, and our bag has a capacity of 8. And we'll make the exact same decision on the right side of our tree as well. If we include it, we'll have a capacity of 6 left. If we don't include it, we'll still have a capacity of 8 left. And if we include the item, we'll gain another profit of 4. If we don't include it, we'll gain a profit of 0 for that decision. Here, same thing, we'll gain a profit of 4 or gain a profit of 0. And now at the third item, it has a weight of 3. Over here now, if we try to include that item, we will get a weight of -2. So essentially what that means is we can't do anything. So we're not even going to put a green value over here. We're not even going to put a 7 over here because that would be misleading. That would mean that this is a valid path, but there's no possible way we can include 7 plus 4 plus 4 because that would be a profit of 15. We know that the real max profit is 12 in this problem. So recursively, that's how we would handle it. We can also choose to not include that item, which would leave us with a capacity of 1 still. Here, same decision, but this time we actually can include that value because we have a capacity of 3 left. We will end with a capacity of 0. There's nothing wrong with having a capacity of 0. It just means our bag is full now. It just means that we can't really continue at this point. But if we don't include it, we would still have a capacity of 3. Here, same exact thing. If we include it, we'll decrement our capacity by 3. Here, if we don't include it, we'll have a capacity of 0. Same thing here. And for each of these, same thing. We can either gain a profit of 7 if we include the value or a profit of 0 if we don't include the value. And at this point, you probably get the idea. So I'm going to run through it quickly. So for this path, we have a capacity of 1 left. We're at the last item. We can include this item or we can not include it. If we do include it, which we have enough capacity for, we will gain a profit of 1 from that item. So plus 1, plus 4, plus 4. So we're going through the whole chain now, seeing, given this possible path, what was the profit that we calculated? It was 9. So 9 is our max so far, I guess. Then we'll go down this path. Here, we have a capacity of 0. So even if we try to include this value, we can't. We don't have enough capacity for a weight of 1. So this is the max we can calculate along this path. If you go up the entire chain, you'll get a 4 plus 0 plus 7. That's 11. So that's our max so far now. Going down this chain, we actually do have enough capacity for that item. So that would leave us with a capacity of 1. Here, we also have enough capacity for it. For each of these, we will also do the path where we don't include it, but I'm not going to draw that out because those won't lead us to the solution anyway. Oh, and by the way, this should have been a 6 over here. Sorry about that. And over here, I'll draw it out. We would have a capacity of 4 remaining. And for each of these branches, we only drew the ones where we do include the item. So for each of those, we'll gain a profit of 1. That was the profit of that item. Now, essentially what this recursive brute force algorithm would do is for each of these, we would just total what was the max we got. So for this one, it was 1 plus 0 plus 0 plus 4. That's 5. For this one, though, this is our max, actually. We got 4 plus 7 plus 1. That's 12. So that actually is the max solution. We would run through all of these branches just to verify that. This one is 8, I think. And, we would have calculated the entire tree. I just wanted to save a bit of space over here. But you can see that when we skip the first item, but we include the other 3 items, so this one, and this one, that leads us to a max profit. We had to run through every single possible scenario though. So this is what the code for that would look like. Maybe it's a bit shorter than you were expecting, or maybe it's a bit longer, but we're given the array of profits. We're given the array of weights. These are of course going to be the exact same size because each index corresponds to a single item. We're also given a capacity that's going to be the size of, our bag. And basically most of the work is going to go inside of a recursive helper function. The reason is because we're going through every single position. So we need an extra argument for the function to pass in the index that we're currently at. The rest of the 3 parameters are going to be passed into that recursive helper as well. And essentially for every single item, we're going to have two choices, whether we include it, which is this case, and whether we skip the item, which is this case over here. And the base case, of course, is going to be when we reach the end of the input over here. And we're handling that over here where, the index becomes this position over here. So when we skip the item, that's really the simple case. We simply call our DFS helper, our recursive function, and all we do is pass I plus 1. We don't have to do anything else. This is the profit, the max profit we can calculate with our helper function when we skip the item. When we include the item is a tiny bit more complicated, and that's because we first have to ensure that we have enough capacity to include the ith item. So we take the current capacity that we have that was passed into our function, subtract the weight of the item that we're trying to include, and we get a new capacity. If the new capacity is greater than or equal to 0, then we're allowed to include this item. So that's what we do. We take the profit of that item, add it with a recursive call, and we're passing in I plus 1 here. And also notice how we're passing in the new capacity because we subtracted this weight from the capacity. So this is the remaining capacity that we have. And we're recursively calculating the max profit with this capacity remaining on the remaining items to the right of this item, for example. The other parameters are going to stay the exact same. The profit and weight are simply arrays. These are never going to be changing anyway. And so this is the profit, the max profit we could calculate with including this particular item. Now we have to find the maximum. If we couldn't include this item at all, our max profit is going to stay the same. But if we can include this item, then we have to calculate the max profit. We're going to take the maximum of the profit we just calculated and the maximum of the previous profit that we calculated. So these two, and then we'll, set the max profit to that, and then we would return from there. Now we can actually take this code, even though it's not very efficient, it's 2 to the power of n, but we can optimize it to actually be big O of n times m time complexity, where m actually is the capacity that we're given. It's kind of unusual to have an integer value input to be a part of the big O time complexity, but that is the case here. We can get this to be the time complexity. Let me show you how we would do that. We actually don't have to modify this code very much at all. We know that obviously 2 to the power of n has the potential to be a really, really large number, especially if, this input array is really, really large. N times m could be a large number, but it's not going to be super, super large. It's not growing exponentially. That's the important thing here. For small input sizes, 2 to the power of n might not be very large, but for super large inputs, it is going to be. When we get really, really large decision trees, it's common that we end up solving the same subproblem multiple times. Like, see how big this tree is getting. Isn't it true that there's probably going to be some duplicate work? Because this level, for example, is going to be maybe the third position over here. It might be true that there's we get to this position where our capacity value is something like 6. And there might be other positions where the exact same thing is happening, right? So we're at index 2, right? Let's say this is index 2 and our capacity is 6. Our remaining capacity is 6, and we might end up solving that same subproblem multiple times, and we might have a bunch of other duplicate subproblems in our decision tree. The way we can eliminate this repeated work is by caching that solution. So if we ever call this function where I equals 2 and capacity equals 6, for example, and it's our first time calculating that, we want to store the result. So then if we ever call this function with the exact same inputs, because remember, these two arrays are never changing. So if we call it with the exact same input, then we don't actually have to do all of this work, because we know this could end up being a lot of work, because it's not just a few lines of code here. We might end up doing more recursive calls. So if we can save ourselves from doing that, it would be really helpful. So that's how we get to caching. Let me show you what I mean. So this is what the caching solution would look like. It's actually not very different at all. Sometimes it's also called the memoization solution. So this time we can reduce our time complexity, and it's because we have a cache. In this case, the cache is a 2-dimensional array. You could also use a hash map if you'd like, but basically the dimensions of this are going to be the dimensions of our input space. Well, in this case, our inputs I and capacity. Because we know if, in this example at least, the capacity is 8 and the size of our input arrays is 4. So all possible values that we could pass in to this function, our recursive helper function, are going to be 4 by 8. Those are all possible inputs we could pass in. So we're representing those inputs with a two-dimensional array. With, for example, the row represents the item that we're looking at. So the row is the item. The column is going to represent the capacity. And actually in this case, the number of columns we have is not just going to be 8, because 8 would be from 0 all the way to 7, but we're actually going to have plus 1 column here. So we're going to go all the way from 0 to 8. We're pretty much going to be ignoring this 0 column. And this, by the way, is just initializing a two-dimensional array in Python by the dimensions I talked about. I'm taking n to be the length of basically the number of items we have, and m to be the capacity that we have for shorthand. And we're initializing the array with all -1s. -1 is just a default value. That tells us that for this particular position, for example, if we had like a -1 over here, and maybe this is where we had a capacity of 2, and this is for item 2, in this position, if it's a -1, that essentially means that we haven't computed the max profit for, passing in these two inputs into our recursive function yet. But if it has some non-1 value here, that means we have calculated it. So when we run our recursive function now, we have that original base case, but we also have a second base case where if the value in our cache for this input, where I is the item and capacity is the remaining capacity, if it's not -1, that means we've already computed this before. That means we don't have to do that recursive work. We can simply return the value stored in our cache. If we're not doing that though, then we have to calculate that value. Now at that point, this solution is exactly the same as the depth first search brute force solution. The only difference is instead of us just calculating the max profit and returning it, we're actually calculating that max profit and storing it inside of the cache. So we store that, and then we also return the max profit as well. But notice how the cache is actually another input variable to this function, because we want a reference to that two-dimensional array. We want to always pass it in every function call. So we do that when we call this function recursively. Now, this is about as efficient as you can get for this problem. And I think in a real interview, if your interviewer is fine with the memoization solution, I would recommend doing this because it's usually easier to code up, even though what I'm about to show you, which is the true dynamic programming solution, is usually less code. It's usually more unintuitive. It's a pretty abstract solution to come up with. But I'm going to show it to you anyway. Sometimes the true dynamic programming solution can be optimized to reduce the space complexity. So in this case, our two-dimensional array is of the dimensions n by m. Sometimes in dynamic programming, you can reduce those dimensions though. So for the true dynamic programming solution, we're going to skip the recursion altogether. We're going to initialize a two-dimensional array of the exact same dimensions typically. So we're going to have 4 rows, 1 for every single item in our input, and we're going to have 9 columns in this case, because we're skipping the 0th column because we still want capacities for 1 through 8. But in this case, the 0th column is actually going to be relevant for us. I'm going to show you why in just a minute. But generally, what this algorithm is going to do is similar to what the memoization solution was doing, the same as the recursive solution, except we're going to be doing it in a particular order, because intelligently we can figure out for this particular position, for example, before we calculate this position, and what this position represents, by the way, is with these 3 items so far, if we have access to these 3 items and we have a capacity of 5, what's the max profit we could get? Going one step below that is with all of these items with a capacity of 5, what's the max profit we could get? Starting at the top left is essentially with only the first item and a capacity of 0, what's the max profit we could get? Well, usually this is going to be 0 because we don't even have any capacity. And actually, if the capacity is 0, 0, then this whole column is going to be 0 because we can't include any items, assuming all of the items have a positive weight. We can't include any items. So our profit is going to be 0 when we have a capacity of 0. Okay, but what about the 0th item? In our case, this is the 0th item. Can we include it when we have a capacity of 1? Nope, because the weight of that item is 5. So here our capacity will again be 0. And same for this one, and same for this one. And we'd keep doing that until we got to the point where we actually do have enough capacity to contain this item. So what would be the max profit in this position, which means if we only have access to this item, what's the max profit we get with this capacity? Well, of course, we would include that single item. That's all we can do. And that's all we can do for all these positions as well. So we would have a total profit of 4. Now, what I just did right now, I'm initializing that with 2 loops. The first column over here is being initialized to all zeros, and the first row over here is being initialized using that logic. First of all, the reason I'm doing this initialization is because it helps us eliminate edge cases when we do the full solution over here. This is a relatively small amount of code, but if we didn't do this setup, we would have a few extra conditionals over here. And this is a good template to follow for most dynamic programming problems, especially, 0-1 knapsack and unbounded knapsack. The thing though is when we initialize our 2-dimensional array, we're not initializing it to -1s. We're doing all zeros anyway. So we actually didn't need to do this first column. The reason I did it is sometimes I prefer to write out DP solutions using a hash map instead of a 2-dimensional array. That can also help eliminate edge cases. So if you were doing it that way, then you would want to initialize the first column like this. Now we actually get to the full solution, and you'll see why we did this initialization in the first place. We're going to essentially go row by row, starting at the first row. We're skipping the 0th row because we know we already did that over here. And then we're going to go column by column. We're going to ask ourselves, if we have access to the first item, but not just the first item, we have access to technically all of these items, every item that came before that one as well. And for this position, we want to choose to include that item or skip that item. What's the max profit we could get if we have a capacity of 1? Well, first of all, the item at index 1 is this item. It has a weight of 2 and a profit of 4. So we have 2 choices, essentially. We can choose to skip that item. If we skip that item, what's the max profit we could get with skipping this item? And assuming we can't access the other items as well, we're basically saying we only have access to the previous item. Well, we can look directly up here. We can see what was the max profit we calculated with a capacity of 1 that did not include this item and it only included this item. Well, that profit was 0. And this is the line of code that we would do that with. If you go back and look at the recursive solution, you'll notice that we actually did this line with a recursive call. We're simply moving it from a recursive call to accessing our DP cache instead. We also have a choice of whether we can include this item or not. We're going to initialize that value to 0 because we don't know if we even have enough capacity to include the item. And in this case, it turns out we don't. We're going to take the weight of the item, which is 2. Our capacity right now is 1. We're going to take 1 minus 2, and that's not greater than or equal to 0, so we can't include this item. So we're going to skip it. And then we would take, the maximum of those 2 values. They were both 0, so we would, set that value to 0 as well. And then when we get here, though, it's going to get a bit more interesting because now we actually do have enough capacity to store the second item. But we're going to look at if we were to skip that item, we would get a maximum profit of 0. So if we skip the item, we get a profit of 0. If we include the item, we have enough capacity to do so, and we get the profit of that item. So the profit of that item is 4, plus we take I plus 1. So we still look in the row above. That's what I plus 1 here means. And we take our capacity, which was 2, subtracting the capacity that we had right now, subtracting the weight of the item that we just added, which was 2. From this position, we would say 4. 4 was the profit of that item, plus the value that's over here. So this is why we had to initialize the first column, because we might end up accessing it diagonally. And this line as well is very similar to the recursive solution. I think we had something almost exactly like it, except this DP was replaced by a recursive call. So the value here would be 0 plus 4, so that would end up being 4. And that's the main idea behind this. We're going to keep going value by value in this row, filling it out, because to fill out these values, we simply need access to maybe the row above it and values to the left of it and, values over here. We basically are only going to look up, left, or top left. So that's why we compute these values in this order. But also notice how we're only going to be going to the I minus 1 row. So no matter where we are, maybe we're in this position, we're never going to go 2 rows above. We're only going to go 1 row above. Same thing over here. We'll only go 1 row above. So do we really need this entire 2-dimensional grid to be in memory? Could we have solved this problem with less memory? In this case, the memory complexity was n times m, but it can actually be solved with even less memory. I encourage you to try to take this solution and optimize it to practice it, because just reading code sometimes is not enough to really get it inside your brain. So I recommend trying to optimize this code. If you can't figure it out, or if you did figure it out, consider posting it on the Discord. But this is the main idea behind this problem. I also encourage you to try to fill out this grid using this algorithm. It'll help you kind of understand what exactly is going on. I'll quickly fill it out right now just so you kind of have the information. These, I believe, will be all 4s because we can only include a single item until we get to a capacity of 7. When we have a capacity of 7, we can include both of the first 2 items. So that will give us a profit of 8. Over here, though, with a capacity of 1, we will have nothing. With a capacity of 2, we can't include the 3rd item, but we can still include the 2nd item. We'll just look up and see, hey, there's a 4 here, so add that. Over here, though, we can include the 3rd item. It has a profit of 7, or we can choose to include the 2nd item. It has a profit of 4. We're, of course, going to choose the one with a higher profit. Here, I believe it will be 7. Here, I believe we can include these 2 items, giving us a profit of 11. Here, it's also going to be 11, and I think we can't really get any higher than 11 until we get the last item. So here, we can include a single item with a capacity of 1, so we'll get that. Here, I think it'll be 4 again. I think here will be 7. Here, I think will be 8 because we can include both of these items with a weight of 4, giving us a profit of 8. This, I believe, will be 11, but when we have a capacity of 6, we can actually include all 3 of these items. That's exactly what we're going to do. We're going to have a profit of 12, and basically what the last position in the grid will represent is using all of these items and a capacity of 8, so we have the max allowed capacity, and we have access to all the items. What's the max profit you can get? So the solution is always going to be in the bottom right position, so this is going to be the return value here. You could also, if you forgot that this is where the solution is, you could, you could have a single variable that is the result variable, and you could, take the maximum of this every single time and assign it to that variable and then return it. But you can also do it like this. So this was a lot to get through. And even if you take a look at this picture and you feel like you know exactly what's going on, when you actually try to code this up on your own, it's really difficult, especially if you haven't practiced it in a while. It can get really, really abstract. There's definitely a lot of edge cases. It's hard to kind of visualize what's going on. Like, what's the items? What's the capacity? What direction are we looking in and all that? But as always, practice makes perfect. And dynamic programming is definitely the type of thing that needs a lot of practice.